Welcome! Today, we'll explore an intriguing problem titled Painting a Grid with 3 different colors. This problem challenges us to determine the number of valid ways to paint a grid under specific constraints. Let's dive into the approaches and strategies to tackle this problem effectively. In this problem, we are tasked with painting a grid consisting of m rows and n columns using 3 different colors. The rules for painting are straightforward yet restrictive. No 2 adjacent cells in the same row or column can share the same color. This means that, for any pair of adjacent cells, whether horizontal or vertical, each must be painted a different color. The challenge is to determine the total number of valid ways to paint such a grid, given the constraints. Since the grid can grow large, with up to 1,000 columns, the result is returned modulo 10 to the power of 9 plus 7 to keep the output manageable. The problem specifies that m can range from 1 to 5, while n can be as small as 1 or as large as 1,000. The output is a single integer representing the total number of ways to paint the grid under these conditions. Let's look at a simple example to understand the problem better. If the grid consists of just 1 row and 1 column, meaning m equals 1 and n equals 1, there's only 1 cell in the grid. This single cell can be painted using any of the 3 available colors, as it has no neighbors to constrain its choice. Therefore, in this case, the output is 3, representing the 3 distinct ways to paint the grid. Now consider a slightly larger grid where m equals 1 and n equals 2, meaning we have 1 row with 2 adjacent cells. To satisfy the condition that no 2 adjacent cells share the same color, the first cell can be painted in any of the 3 colors, but the second cell must be painted in a different color. This gives us 6 valid combinations in total. The first cell can be painted with color 1, 2, or 3, and the second cell can be one of the other 2 remaining colors. Listing them out, the possibilities are color 1 with color 2, color 1 with color 3, color 2 with color 1, color 2 with color 3, color 3 with color 1, and color 3 with color 2. Hence, the output is 6. When we scale up the grid to include multiple rows and columns, the number of valid configurations grows significantly. For example, in the case of a 5x5 grid where m equals 5 and n equals 5, there are numerous valid ways to paint the grid that satisfy the adjacency constraints. Here, the problem requires efficient computation, as directly enumerating all possibilities would be infeasible. After applying the necessary calculations, the total number of valid ways to paint this grid turns out to be 580,986. This result is provided modulo 10 to the power of 9 plus 7, as specified in the problem statement. To solve this problem effectively, we need to utilize dynamic programming. The key observation is that while m is small, the number of columns, n, can be very large, making a direct enumeration approach impractical. Instead, we can define states based on valid configurations of individual rows and compute transitions between these states as we progress column by column. By carefully tracking these states and ensuring that adjacent rows and columns adhere to the painting rules, we can efficiently calculate the total number of valid grid configurations, even for large values of n. This approach ensures the solution remains computationally feasible within the given constraints. To begin tackling this problem, we first considered the brute force approach. The intuition here is straightforward: generate all possible ways to paint the grid and then filter out any invalid configurations. Since each cell can be painted in one of 3 colors, the total number of configurations grows exponentially with the grid size, specifically 3 raised to the power of m times n, where m is the number of rows and n is the number of columns. However, this method quickly becomes computationally infeasible as the grid size increases. The key challenge lies in the constraints: each cell's color depends on its neighbors, both to the left and above, and ensuring no 2 adjacent cells share the same color requires significant validation. This results in an exponential time complexity of 3*m*n, which is not scalable for larger grids. Recognizing this limitation, we explored a more efficient approach: dynamic programming with state compression. The core idea here is to represent each row as a state based on its coloring and build valid configurations row by row. By encoding the colors of a row into a single number, we can systematically transition between states while ensuring validity. This approach significantly reduces redundant computations and offers a structured way to solve the problem. Dynamic programming with state compression offers several advantages by leveraging the problem structure. First, we can pre-compute all valid states for a single row, which is limited to 3 to the power of m, possible states since no two adjacent cells in a row can share the same color. Then, the transitions between rows depend only on the compatibility of their respective states, which involves 3-2m combinations. This means we can compute the number of valid configurations for the entire grid by iteratively transitioning between rows in a way that respects these constraints. This drastically reduces the problem size compared to brute force. The complexity of this approach is n*3-2m, where n is the number of columns, and it is efficient for grids with a small number of rows. While alternative methods like DFS or backtracking could be used to explore configurations, they essentially mimic brute force with some pruning and lack the efficiency of DP with state compression. By focusing on row-to-row transitions and pre-computing valid states, DP provides a structured and scalable solution to the problem. Ultimately, the chosen strategy is dynamic programming with state compression because it strikes the right balance between efficiency and conceptual clarity. Brute force is computationally infeasible for larger grids, while DFS or backtracking are not efficient enough to handle the problem's constraints effectively. DP, on the other hand, capitalizes on the grid's inherent structure, specifically, the dependencies between rows and their states. This minimizes redundant computations by reducing the problem to transitions between pre-computed row states. One trade-off of this approach is the space requirement, as the DP table requires n*3 to the power of m storage. Additionally, while the time complexity of n*3-2m is manageable for small m, it can still become challenging as m increases. The key insight, or aha moment, was recognizing that the problem could be reduced to state transitions between rows instead of focusing on individual cells. This drastically reduced the search space, making DP with state compression the most practical and scalable solution given the constraints. By leveraging these insights, we ensure an optimal balance between performance and feasibility for solving this problem. To solve this problem, the first step is to deeply understand the requirements. We have a grid of size m by n, where each cell can be painted in one of three colors. The key constraint is that no two adjacent cells, either horizontally or vertically, can share the same color. The objective is to calculate the total number of valid ways to paint the grid while adhering to these rules. Now, a brute force approach might seem like a natural first step. This would involve generating all possible color combinations for the entire grid. Since each cell has three color choices, for a grid of size m by n, there are 3 raised to the power of m multiplied by n combinations. We would then check each combination to verify if the adjacency constraints are satisfied and count the valid configurations. However, this approach quickly becomes infeasible due to its exponential complexity. For example, even a modest grid size of 5 by 5 leads to over 847 billion combinations. Checking each of these combinations is computationally prohibitive, so we need a more efficient approach to tackle this problem. To address the inefficiency of the brute force method, we turn to dynamic programming, which allows us to optimize the solution by avoiding redundant computations. The idea is to define a state based on the coloring of a single row and then calculate how this row interacts with adjacent rows. Transitioning between these valid row states efficiently is key to reducing complexity. To represent these row states, we can use strings or binary numbers, where each digit corresponds to the color of a cell in the row. A row is considered valid if no two adjacent cells have the same color. The next step is to pre-compute all valid row states for a single row of length n. This can be done using a backtracking algorithm that ensures no two adjacent cells in the row share the same color. These valid states are then stored in a list for quick and efficient access. With this setup, we can define our dynamic programming transitions. The DP I state represents the number of ways to paint the first I rows such that the ith row is in the given state. To compute transitions between states, we iterate over all valid states of the current row and check their compatibility with the states of the previous row, ensuring the constraints are met. The dynamic programming process begins with the base case. For the first row, we initialize DP1 state to 1 for all valid states, because any valid row configuration is possible at this point. From there, we use a recursive relation to build the solution row by row. For each row starting from the second, and for each valid state of the current row, we sum the values of compatible states from the previous row. This relationship can be expressed as DP I current_state plus equals dp, I1, previous underscore state, where the previous state is compatible with the current state. Once we've processed all rows, the final answer is simply the sum of all dp, m, state, values for the last row. This approach introduces several key insights. By compressing the states of each row into integers, we significantly reduce the problem's complexity. The number of valid row configurations is much smaller than the total number of possible combinations, making this feasible. Additionally, pre-computing the transitions between valid states ensures that we avoid redundant checks during execution, further speeding up the algorithm. Lastly, for edge cases like single row or single column grids, the problem simplifies and can be solved directly without the need for dynamic programming. To implement this solution, we rely on several key data structures. First, the dynamic programming table, or DP table, is a 2D array that stores the number of ways to paint up to row I given a specific state of row I. Its dimensions are m rows by the number of valid states. Next, we use an adjacency list to store compatible transitions between valid row states. This adjacency list is pre-computed, which allows us to quickly determine which states can follow one another without recalculating compatibility on the fly. Finally, we maintain a list of all valid row states, generated using a backtracking algorithm. This list is used to iterate through possible states during both the pre-computation and the dynamic programming steps. These data structures work together to efficiently calculate the total number of valid grid configurations. The algorithm involves several critical operations. First, backtracking is used to generate valid row configurations. By recursively constructing rows one cell at a time and ensuring adjacent cells differ in color, we can systematically create all valid rows. Next, we compute transitions between rows. This involves comparing two rows to ensure no two vertically adjacent cells share the same color. For efficiency, we can use bitwise operations or simple array comparisons to perform these checks. The core of the solution is the dynamic programming loop, where we iterate through the rows and their states, updating the DP table based on the pre-computed transitions. Finally, to obtain the result, we sum all the values in the last row of the DP table. This aggregation gives the total number of valid configurations for the grid, completing the computation efficiently. To tackle the problem of painting the grid, we start by defining a function color the grid inside our solution class. The first step is to generate all valid row patterns for the grid. This is done through a helper function generate_valid_rows, which uses recursion. The function ensures that no two adjacent cells in a row have the same color. By iterating through three possible colors and checking against the previous cell's color, we systematically build all valid row combinations. These combinations are stored as tuples in the valid_rows list. Once we have all valid rows, the next step is to check for compatibility between rows. A pair of rows is considered compatible if no cells in the same column across those rows share the same color. The helper function r_compatible performs this check by iterating through every cell in the rows and returning false if any corresponding cells have the same value. Using this, we pre-compute the compatibility relationships between all valid rows. This is stored in a dictionary called compatibility, where the key is the index of a row, and the value is a list of indices of compatible rows. Now that we have pre-computed the row compatibility, we move on to the dynamic programming solution. To optimize our approach, we use memoization with Python's at ru_cache decorator. This allows us to store results of previously computed states and reuse them, avoiding redundant calculations. The function dp is defined to represent the number of ways to color the grid starting from a specific column and a given previous row. If we reach the last column, the base case is satisfied, and we return 1, as that represents a valid configuration. Otherwise, we initialize a counter total_ways to accumulate the number of valid configurations. For each compatible row for the current column, we recursively call dp for the next column while passing the compatible row index. Finally, we sum up the results from all valid rows for the first column using the dp function initialized at column 1. This gives the total number of ways to paint the grid, which is returned as the solution. In this implementation, we begin by defining the main method, color the grid, which takes the dimensions of the grid, m for the number of rows and n for the number of columns. The first step is to generate all valid row patterns for the grid. These are rows where no two adjacent cells have the same color. This is achieved using the helper method generateValidRows, which recursively constructs valid row configurations based on the constraints. The results are stored in the valid rows list. Next, we pre-compute the compatibility between all pairs of valid rows. Two rows are considered compatible if they meet the condition that no column in one row shares the same color with the corresponding column in the other row. This compatibility is stored in a map, where each valid row is associated with a list of other rows it can pair with. Finally, we set up the dynamic programming table, DP, where DP, call, row, holds the number of ways to paint up to the call th column with the row th valid row at the top. The base case initializes the first column with one way for each valid row, as there are no previous columns to consider. Now, the dynamic programming logic iterates through each column starting from the second. For each valid row in the previous column, we calculate how many ways we can transition to compatible rows in the current column. This is done by updating DP, call, next row, adding the ways from DP, call 1, prevrow, for all compatible next row values. The modulo operation ensures that the values remain within the constraints of the problem, avoiding overflow while adhering to the modulo 10000000007 requirement. After building the DP table, the last step is to sum up all the ways to paint the grid for the final column. This gives us the total number of valid ways to paint the entire grid. The result is stored in the variable result and returned. This dynamic programming approach ensures that we efficiently calculate the solution by breaking the problem into overlapping subproblems and reusing computations. The helper method generateValidRows recursively generates all valid row configurations for a grid of m rows. It ensures that no two adjacent cells in a row have the same color. By iterating through all possible colors and backtracking when necessary, it builds up a list of valid row patterns. Additionally, the are-compatible method checks whether two rows are compatible. It compares the colors of corresponding cells in two rows and returns false if any of them are the same. This ensures that adjacent columns in the grid meet the problem's constraints. Together, these helper methods play a crucial role in generating valid configurations and verifying their compatibility, enabling the dynamic programming approach to work seamlessly. To solve the problem, we start by looking at a small grid example where m equals 2 and n equals 1. In this case, each row consists of two cells, and each cell can be painted with one of three colors, 0, 1, or 2. The key constraint is that no two adjacent cells in a row can have the same color. To generate all valid rows, we use a recursive approach. We start with an empty row and try adding colors one at a time. For instance, if the first cell is painted with color 0, the second cell can only be painted with color 1 or 2. This gives us rows like 0, 1, and 0, 2. Repeating this process for starting colors 1 and 2, we end up with 6 valid rows, 0, 1, 0, 2, 1, 0, 1, 2, 2, 0, 2, 1. Next, we pre-compute compatibility between rows. Two rows are compatible if their vertical cells, meaning cells in the same column, do not share the same color. For example, the row 0, 1 is compatible with rows like 1, 0, and 2, 0. We store these relationships in a dictionary, where the key represents the index of a row and the value is a list of indices of compatible rows. Now, we move on to dynamic programming to calculate the number of ways to paint the grid. The idea is to use a function dp, call, prev_row, that computes the number of valid ways to paint the grid starting from column call, given that the previous column is represented by prev_row. The base case is simple. If the column index call equals n, the total number of columns, we return 1, as we've successfully painted the entire grid. For the recursive case, we iterate over all rows that are compatible with prev_row and sum up the results of dp, call plus 1, next_row. This way, we build the solution column by column, ensuring compatibility between rows. To initialize the process, we consider all valid rows as potential first rows and sum up the results of dp, 1, I, for each valid row I. For our small grid example with m equals 2 and n equals 1, the final result is 6, meaning there are 6 distinct ways to paint the grid while adhering to the constraints. Next, let's examine a larger grid example with m equals 2 and n equals 2. The valid rows remain the same as in the previous example: 0, 1, 0, 2, 1, 0, 1, 2, 2, 0, 2, 1. Compatibility between rows is also pre-computed in the same way, ensuring that no two vertically adjacent cells share the same color. In the dynamic programming step, we once again calculate the number of ways to paint the grid column by column. For the first column, we start with all valid rows. Then, for each row in the first column, we consider only the compatible rows for the second column. Using the function dp, call, prev_row, we recursively compute the total number of ways to paint the grid. For example, if we start with row 0, 1 in column 1, we calculate dp, 2, next_row, for each row compatible with 0, 1. Summing up all configurations for every possible starting row, we find the total number of ways to paint the grid. For m equals 2 and n equals 2, the result is 54. Finally, let's consider a taller grid with m equals 3 and n equals 1. In this case, valid rows are longer, as each row now consists of 3 cells. Using the same recursive generation method, we ensure that no two adjacent cells in a row have the same color. This results in a total of 12 valid rows, such as 0, 1, 2, and 0, 2, 1. Compatibility between rows is also pre-computed. For example, the row 0, 1, 2 is compatible with 1, 2, 0, but not with itself, as adjacent vertical cells must differ in color. Since the grid has only one column, n equals 1, the total number of ways to paint the grid is simply the number of valid rows. Therefore, for m equals 3 and n equals 1, the result is 12. This demonstrates how the approach scales to different grid dimensions, ensuring that we can handle both wider and taller grids efficiently. To analyze the time complexity of our solution, we start by looking at the process of generating valid rows. Here, we use a recursive function to construct row patterns of length m, ensuring that no two adjacent cells have the same color. While each cell has 3 possible colors, the adjacency constraint effectively reduces the branching factor to 2. This results in about 2m valid rows. Since the recursive process involves appending and copying rows, the total time required for generating these rows is m*2 to the power of m. Next, we consider the pre-computation of row compatibility. For each pair of valid rows, we check if they can coexist by ensuring no two cells in the same column share the same color. With about 2m valid rows, there are approximately 4m pairs to check. Each compatibility check takes m time, leading to a total complexity of m*4 to the power of m for this step. These two components set the foundation for the overall time complexity. The final and most significant step in our solution is the dynamic programming process. Here, we compute the total number of ways to paint the grid column by column. For each column, we iterate through all valid rows, which involves 2 to the power of m rows, and transition to compatible rows using the pre-computed compatibility list. This transition process occurs for n columns, with each row having up to 2 to the power of m compatible transitions. As a result, the DP step requires n*4 to the power of m time in total. When we combine all these steps, the overall time complexity of the solution is dominated by the DP step and compatibility pre-computation, leading to a total complexity of m times 4 to the power of m plus n times 4 to the power of m. For cases where m is small relative to n, this simplifies to approximately n*4 to the power of m. Next, we examine the space complexity of the solution. The first factor is the storage of all valid rows. Since there are 2m valid rows, each of length m, this requires 2 to the power of m*m space. Additionally, the compatibility list, which stores compatible rows for each valid row, takes 4 to the power of m space because we need to account for 2m rows, each with up to 2m compatible counterparts. Finally, we have the memoization cache used by the dynamic programming function. This cache stores results for all states, defined by the column index in the previous row, resulting in n*2 to the power of m states and a total space requirement of n*2 to the power of m. Together, these components contribute to the overall space complexity. When we aggregate the space requirements, the total space complexity becomes 2 to the power of m times m plus 4 to the power of m plus n times 2 to the power of m. However, for large values of m, the O, 4 to the power of m, term dominates, making it the primary contributor. To better understand the efficiency of the optimized approach, we can compare it to a brute force solution. A naive method would involve generating all possible colorings of the grid, which amounts to 3 m*n combinations for an mxn grid. Checking the validity of each coloring would take O(m*n) time, resulting in an overall time complexity of O(m*n 3 m*n). This is clearly infeasible for large inputs. In contrast, the optimized solution reduces the complexity to O(n*4 to the power of m by leveraging valid row generation, compatibility pre-computation, and dynamic programming, making it far more practical when m is small and n is large. To summarize, the optimized solution achieves a time complexity of O(m times 4 to the power of m plus n times 4 to the power of m, which is dominated by O(n*4 to the power of m, for small m relative to n. The space complexity is O(4 to the power of m, reflecting the storage requirements for the compatibility list. In comparison, a brute force approach would have a time complexity of O(m*n 3 m*n and a space complexity of O(1). Clearly, the optimized approach is a significant improvement, especially for cases where the grid has a small number of rows but many columns. This efficiency highlights the power of leveraging dynamic programming and pre-computation to solve complex problems effectively. When solving grid problems like this one, there are a few common mistakes to watch out for. First, assuming all configurations are valid can lead to inaccurate solutions. Remember, constraints like ensuring adjacent cells don't share the same color drastically reduce the number of valid combinations, so it's essential to filter out configurations that break these rules. Next, overlooking recursive overlaps can be problematic. Each row or column in the grid is not independent, they're constrained by the configurations of previous rows or columns. This dependency means you'll often need dynamic programming to manage overlapping subproblems effectively. Finally, using an inefficient state representation can make your solution impractical. For example, representing the grid with a large 2D array instead of a compact, encoded state can drastically increase memory and computation requirements. By addressing these issues, you can avoid unnecessary inefficiencies and errors in your approach. Another common mistake is relying on brute force for large grids. While it may seem straightforward to generate all possible configurations, the exponential growth of possibilities, about 3 to the power of the number of cells, makes this approach computationally prohibitive as grid sizes increase. It's crucial to incorporate pruning or optimization to make your solution feasible. Additionally, misunderstanding how to apply the modulo operation consistently can lead to incorrect results. Many grid-related problems require results to be returned modulo 10 to the power of 9 plus 7 to prevent overflow. Forgetting to apply the modulo at intermediate steps, or applying it incorrectly, can break your calculations. Paying attention to these details ensures your solution is both efficient and accurate for larger grids. To excel in interviews, it's helpful to view grid painting problems as state transition problems. Dynamic programming is a powerful tool here, and a well-defined state representation, like encoding a row's configuration into an integer, can simplify the problem significantly. Looking for symmetries or patterns is another key insight. For instance, if the grid has symmetrical properties, you can reduce computational effort by focusing only on unique configurations. When evaluating time complexity, it's important to consider the size of the state space and the number of transitions between states. Effective pruning can dramatically reduce the search space. Lastly, always clarify constraints during interviews. For example, confirm whether diagonal adjacency rules apply or if the constraints are limited to rows and columns. These insights will not only help you solve the problem but also demonstrate a structured approach to problem solving. For additional practice, related problems like LeetCode 790, domino and tramino tiling, or LeetCode 1155, number of dice rolls with target sum, are excellent resources. There are several approaches you can use to solve grid painting problems. The brute force method involves generating all possible configurations and filtering out the invalid ones. This approach is simple to implement but computationally expensive, especially for larger grids, where the complexity grows exponentially with the number of cells. A more efficient alternative is dynamic programming with state compression. By using techniques like bit masking or integers to represent the configuration of a row, you can significantly reduce both time and space complexity. This approach transitions between states efficiently and scales well for larger grids, though it comes with increased implementation complexity. Another option is backtracking with memoization, where you recursively try all valid configurations while caching results to avoid redundant computations. While easier to implement than dynamic programming, backtracking is generally slower for larger grids, making it less suitable as grid sizes grow. Each of these techniques has its trade-offs, so the choice depends on the problem constraints and requirements. For advanced problems, matrix exponentiation is another powerful approach. This method involves representing transitions between states as a matrix and then using matrix exponentiation to compute results efficiently for large grids. It's especially useful when the problem involves repetitive patterns or when the number of rows is very large. The main advantage of this approach is its speed for certain types of problems. However, it requires a strong understanding of linear algebra and is limited to specific grid problems where transitions can be modeled effectively as a matrix. While this technique may not be necessary for most interview problems, mastering it can give you an edge in competitive programming or advanced algorithm design scenarios. Great job! We've covered the problem painting a grid with 3 different colors, explored the brute force approach, and discussed its key aspects. Remember, understanding the basics is crucial before diving into optimizations. Keep practicing, and we'll see you next time. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!